Okay, let's continue with what I have started yesterday, and I just want to remind you of, the main important point that I try to make, that you can tune a phase transition from a superfluid to a self-organized superfluid phase in an atom cavity system. And just to remind you, what that meant was that we have a bunch of atoms between two mirrors. We pump them with a standing wave. And if we crank up the power above critical value, then something dramatic happens. All of a sudden, scattering becomes possible, initiated by some fluctuation, and the scattering builds up a light grating as well as a material grating that are commensurate in the sense that the light grating supports and stabilizes the matter grating, and the matter grating again leads to a situation where the Bragg condition is fulfilled for 90-degree scattering. Stationary deep optical lattice is created in the resonator. That was the last scenario I was trying to point out to you. And now I want to go on and asking the question, what happens if I add a second frequency component of the pump, such that you can imagine that the two pump components together produce something that you could interpret as amplitude modulation. So there's a beating between the two pump waves, which are at slightly different frequencies. And what can we do with these kind of modulation techniques? And this is inspired by basically the fact that modulating optical lattice potentials is very spread among quantum gas experimentalists and theorists, because it has turned out that you can do a lot of interesting things, making lattices more interesting by inducing so-called artificial gauge fields. And that has been leading to optical lattices that have non-trivial topology, which is not necessarily possible without these kind of additional techniques. The typical band structure in the lowest band of an optical lattice is necessarily has trivial topology. So by introducing phases that come with tunneling processes induced by shaking the lattice, you can make much more interesting and complicated effective lattice models. That's something that has been done in conventional optical lattice for long. And another inspiration is that there are experiments indeed where people do similar things with condensed matter systems, and one example is high-TC cuprate systems, where people like Andrea Cavalieri, they are using intense infrared pulses that they shine on cuprate compounds, and what they find is that for a short time they can make these compounds superfluid or superconducting in this case above TC. That's obviously interesting. If you can turn that in a continuous situation, that would be technologically extremely relevant, if you could even go to room temperature like that. And I want to point out to you how this is related to the cavity system that that I've introduced to you. So let's look for two transparencies at light-induced superconductivity. I'm not really an expert on that, so if you ask me two specific questions, I will have to point at other people, but well, I can tell you a few things that I've learned about that. This is the phase diagram of a compound called LESCO, and well, that is a temperature axis. This is a temperature axis here, and this is the axis parameterizes doping. So what happens is that you can exchange lanthanum by strontium to some degree, and the fraction x is parameterizing the x-axis here. And what you see is that at low temperatures, there's a region here where the system becomes superconducting. However, at a certain doping x, which is exactly at the value 1/8, there is a place where Tc basically goes down to very low values, such that typically at this doping the system is not superconducting anymore, but the commensurate doping that you have here leads to, this is what the people claim. I don't know how well they really understand it in detail, but that's the language they use. They say that there's a Wigner crystallization that happens at this doping, such that the electrons arrange in a spatially ordered way, which basically means a charge density wave is coming to existence, which is the dominant phase there, and suppressing the subdominant superconducting phase. So, and now the interesting thing happens. Andrea is shining in an infrared pulse that is basically close to a resonance of a phonon, and the system that I'm talking about is a kind of layered system where you have copper oxide planes stacked, one on top of the other, and the infrared pulse sort of excites a stretch mode, a phonon that sort of moves the copper oxide planes closer and further away, and closer and further away. And doing that, they can make the system at this point in the phase diagram to be superconducting again. For a short time. So what are the ingredients here in the system? There is a charge density wave that is dominant at a certain doping, and by shining in this light pulse, which means they are shaking their lattice, they can make the system superconducting, so to speak, bringing up the subdominant superconducting phase again. And now one can relate this situation to the situation in our cavity. We have a charge density wave, if you want. There's no charge, but there are particles, so we have a particle density wave. That's the self-organized phase. And we have a superconducting phase. This is the phase where we do not scatter and we just have a Bose condensate. That's the two phases. The question now is whether we can suppress our self-organized phase, which corresponds to the charge density wave in the high Tc case, by shaking our pump wave. That's the analogy I'm trying to make. So here you see sort of putting the two systems together. On the left side, the LESCO system. On the right side, the BC plus cavity. In the LESCO system, we have superconducting order and charge density wave order. And here we have superfluid order. This is the non-scattering phase, and particle density wave order. That's a self-organized phase. And in the LESCO system, it's Coulomb interaction that you can adjust via doping that brings about the charge density wave order at a certain doping where on the BC cavity system, we have a photon-mediated long-range interaction, which we adjust by the DC pump. That's the analogy. And yeah, then the interesting question is, on the left-hand side, light-induced superconductivity, does it have an analog in our system with the BC in a cavity? Okay, and well, that's now back to the atom cavity system. This is the protocol of what we're doing. We are first increasing our DC pump to a certain value, and then after some time we are putting on the modulation, which is simply done by introducing a second frequency in our pump wave. And what you see here is a mean field calculation, a simple mean field calculation. Here you see what happens in terms of the cavity, the photon number in the cavity. So as we crank up the pump, at some point we are going into the particle density wave, or if you want, into the self-organized phase. So we see all of a sudden that a light field, a lattice, is building up. And now the modulation starts, and as you see, the photon field in the cavity is suppressed, and we're going back to a cavity which is empty, with no photons. And this is the matter side. You see the different momentum components, how they behave as this is carried out. And you see that the BC mode, the 0, momentum mode, here as you crank up the pump power, at some point when the transition occurs, the BC mode is depleted to some extent, and then here you see that it's sort of revived once you turn on the modulation and suppress the photon field in the cavity. And these are higher order momentum components that you can also look at. So if you care for an analytical model that can be made by theorists, they can write down a Magnus expansion and look at the system in terms of a effective time-independent Hamiltonian with renormalized parameters. And the renormalized parameters that occur in this effective theory is the detuning. That's the detuning of the pump wave with respect to the cavity resonance. And the detuning is increased by the modulation. This is the modulation index, the strength of the modulation that is applied. And also the pump strength of the DC pump is decreased by means of the modulation. So that gives a little bit of insight what is happening here. And then you can, or the theorists can calculate the phase diagram. So there's the modulation strength and the DC pump strength, and you see that there's a phase transition between the BC mode and the density wave mode here. So the question now is, does that work out in experiment? And in fact, it does. So here is the experimental procedure shown. At this point, the DC pump strength is increased, and at this point here the modulation starts with 50 kilohertz. So there are two frequencies in the pump at that point, 50 kilohertz apart. And you see what happens in the experiment. We are looking at the intercavity photon number here for 3 different modulation indices. This is without modulation, the black curve, and you see that here at this point we are running into the particle density wave phase. So this is when the lattice self-organizes in the cavity, and then at this point, since we have no modulation, the level of photons in the cavity is constant, while if we have modulation, you see that we are now starting to suppress the intracavity field, and we can go down all the way to 0. And this is a more complete picture where we have, I think, 13 or 14 different values of the modulation index on the y-axis, and this is time, and this is also an axis that shows you the strength of the DC pump. So the experiment is done by just changing linear in time the DC pump strength as time proceeds. And this shows you the data along this line here when the modulation index for a given instance of time is increased, and you see how the photon number is going down. The momentum spectra that you can look at appear like that with zero modulation index, no modulation. That's the typical momentum spectrum you see in the particle density wave phase. And now, as modulation gets stronger, you see that, these Bragg peaks here disappear. The BC gets sort of restored. The atoms go back to the zero momentum component. And interestingly, also the incoherent fraction of atoms that you see here around the BC mode, part of that also goes back to the BC mode. So there's a truly efficient restoration of coherence in the system by shaking, which is kind of counterintuitive, that you shake a system, and by shaking the system, you increase coherence. Yeah, this is the data in more detail. These squares show the restoration of the BC mode, the zero momentum mode. You see as the modulation grows, the modulation strength grows, more and more atoms return to the BC mode. And then we have the incoherent fraction. This is all the atoms that are in this incoherent distribution except what's in the BC mode. This can be sort of extracted from pictures like that, and you see how this incoherent fraction of atoms is reduced again as the modulation is increased. Well, the red data here, this is the photon number in the cavity. You see the photon number in the cavity is reduced, and this F1, this is these circles here. This is the fraction of atoms in the plus minus 1 h bar k Bragg peaks. These are these peaks here, and they also are reduced. So that is already the summary of basically all the things I've told you about our rubidium cavity. There's quite a lot more that I could show you that does not fit within the time I have. Well, to summarize that, I could read to you all the different things I've tried to tell you, which I will not do because you can read it yourself. But I want to say two things about the future of what kind of things we might be doing in the system. One is to look at metastable subradiant order. This is something that well, occurs if you tune the system into the particle density wave phase, where you have the self-organized lattice, and then shake the lattice at certain frequencies. Then, instead of suppressing the light field in the cavity, you can also excite certain states, which turn out to be suppressing the cavity light field completely, but these states are metastable in the sense that the matter organizes, self-organizes in a structure that prevails, that is stable. And we want to look at that and have done that already to some extent, but these are ongoing experiments. And then we want to look at time crystal dynamics. This is looking for dynamic states of the system where basically the lowest energy state is a dynamical state where you have an oscillation of some observable, which is intrinsic in the sense that it's the system that creates the frequency that you see. And there's already a little bit of theory in this paper where we've looked at the system when the pump wave is blue detuned with respect to the atomic resonance. All the experiments I've shown you had red detuning of the pump waves with respect to the atomic resonances. And there's a prediction that there's an interesting playground to look at such kind of situations when you get a time crystal. So now I want to switch gears and talk about for like another 20 minutes maybe or so about superradiant lasing. And we do that using a narrowband intercombination line using calcium atoms. So I've seen that many of you are involved in similar projects, or some of you are involved in similar projects, mostly dealing with strontium. That's the favorite atom of most people. We are using calcium, which has some drawbacks, but also some quite nice aspects as well. So what is a superradiant laser? Probably I don't have to tell you much about that. Conventional lasers operate in the good cavity regime. That's the situation when the cavity bandwidth is far below the gain bandwidth. And well, in that case, the cavity has basically two roles. It acts to shape the spatial mode. So you get a directed output if you use an optical cavity. And it also is responsible to provide coherence. So basically the flywheel in that system that stores the coherence is the cavity and the photons going back and forward in the cavity. Yeah, clearly then the laser line width depends on the length of the cavity, and well, I don't have to go into details. You all know that there are limitations to the spectral output of such lasers because you have to keep this mechanical length very, very stable. And I mean, I have to say there are people who are really, really good in doing that, and it will be really, really hard to surpass what these people can do. Like you have heard about cryoresonators, which are really fantastic. So nevertheless, one can dream of following the concept of going to superradiant lasers to maybe be able to have a laser that does not depend, with a frequency that does not depend on a mechanical length. So that's the motivation of going into this. Yeah, that's this approach where you have, instead of a good cavity laser, you have a bad cavity laser. And this is basically synonymous to a superradiant laser in my eyes. I don't know whether there's a need for any more fancy definition. In the bad cavity regime, the coherence is stored in the gain medium, so it's the narrow band gain medium that provides coherence. The cavity is still needed because it basically it still is needed to shape the mode and to get a directed beam to have feedback. Yeah, there are many fantastic works on these kind of lasers already, which I'm not going to touch, but rather tell you about our calcium work, which does not mean that I'm not aware of the fact that these guys are much earlier than us. We are kind of following a development that has been going on for a couple of years. So what are we doing at the moment? We basically have or look at the pulsed regime, and the simplest version of that is to have some means of producing instantaneous inversion of kind of a two-level system. So at some instance of time, all the atoms we have are put to the upper state. That's the idea. And then we look what happens, and what happens means what happens if the atoms are placed in a cavity which is resonant to this transition. And well, the expectation is that instead of the usual expectation of exponential decay, you should get superradiance, which means that instead of this long time exponential decay, you get a very short pulse instead, which has a peak size that scales with n squared, square to the particle number, and then you can calculate other properties of the pulse that you expect to be emitted. One is the mean pulse delay time. I will come back to that later, which well, can be calculated approximately to scale with logarithm of n divided by n. And then, yeah, the expectation is that these kind of classical pulses, these are really strong light pulses, that these pulses must be somehow initiated by a first spontaneous photon. So you see that these pulses, the peak of these pulses come after some delay time, and there's obviously the expectation that for a given particle number there is a certain mean delay time that you may expect, but if you look at single shots, then the expectation is due to the fluctuation of the arrival times of the initiating a spontaneous photon, the first spontaneous photon that triggers a pulse, there will be a fluctuating delay time, and these are things that we have been looking at in our experiment, and I will show you how that comes out. So first I have to tell you a little bit about the calcium level scheme. Those people who work with strontium will not be surprised. It's kind of the same, but there are some small differences that can be appreciated. So, well, the line that we used for the lasing is this intercombination line. It's not the narrowest line that you can have. We're connecting singlet S0 to triple P1, and well, the line width here is 375 hertz. So it's not like strontium where you would have 7 kilohertz, but it's also not like magnesium. I think the magnesium analog would be around actually only a couple of hertz, I think. So there's obviously other intercombination transitions that are much more narrow. For bosonic calcium, we also could go to 3p0, and there basically the transition matrix element is 0. But in principle, by adding a magnetic field and mixing in a little bit of 3p1 with the 3p0 state, you could engineer a finite line width. This is something that has been shown by NIST people. Leo Hurlberg and others have shown that this is possible. So one could go to like millihertz or 100 millihertz lines, but we are not yet there. We are still working with the 375 hertz line. Okay, so how do we prepare inversion? I will tell you a little bit about that. Well, to understand the Gauss picture, we need this full, unfortunately, this full diagram. So we start with atoms that are hot and have to be decelerated with a Zeeman cooler using the singlet line at 423 nanometers. This leads to this allows Doppler cooling down to a couple of millikelvin temperatures, so this is not very cold. But there's a nice sort of circumstance here. This transition is not completely closed, but via this D state, we have a decay of atoms into the 3p1 and the 3p2 states. And this channel leads back to the ground state via emitting red photon, and by making the Mott beams large enough, you can recycle these atoms into the Mott. So you can sort of close this lost channel, which you don't want, and just keep this lost channel that brings the atoms into 3p2. So in this way, all the atoms that are well, sort of caught by the Zeeman slower and produced into the 3D blue Mott, they end up as 3p2 atoms eventually. And here we have a nice transition at about 2 microns that connects to 3D3. This is a closed cycle transition with 60 kilohertz line width, and that we use to superimpose a second magneto-optic trap. So then we have a kind of a continuously loaded 3p2 magneto-optic trap. This is our starting point where we already have the atoms at typically 150 microkelvin. 10 to the 9 atoms is kind of this stationary population of the Mott in the 3p2 state. And then there are 2 steps needed to create inversion on the 3p1 upper laser level. And this is explained in these pictures here. So the first step is the following. So we have a 3p2 Mott. This is a sort of, well, I try to sketch that with this glowing ball of atoms in the 3p2 state here, right? Now we have a cavity around this region where the 3p2 Mott acts. And there are a number of things that have to be said here. First, we need a magic lattice. And magic means magic with respect to the transition that we want to use for our laser. So this is a laser at 800 nanometer about that's coupled to the cavity and makes a fairly deep lattice. So this lattice is always there. And then it turns out that it's not possible to immediately, via the 3p2 Mott, load the atoms into that lattice. This is an unpleasant circumstance due to the fact that the 800 nanometers, they disturb the upper state of the Mott. The 3D3 state is strongly shifted such that the Mott frequency shifts into the blue detuned region. Which means that all the atoms that go to this lattice eventually are heated, which is no way to load the lattice. So what we do, we cannot directly load atoms from the 3p2 Mott into the magic lattice and then pump them to 3p1. We have to make a little detour. The detour is to pump the atoms to 3p0. And we are doing that by inserting pump lasers using these transitions here. We pump the atoms up to another 3p1 state. This is a frequency wavelengths around 430 nanometers, and then optically pump the atoms to to the 3p0 state. And this is done in a selective way. It's spatially selective, only well within the magic lattice. There's the pump beam that does that, and the pump beam is extremely weak, such that only atoms that are very slow flying through this region can be pumped. So there's also an energy selectivity, and this lets us load a magic lattice in the 3p0 state with temperatures on around 100 microkelvin about. So at the end of this step, we have typically a couple of 10 to the 6 atoms at, say, 100 microkelvin in the 3p0 state. So now we are not there, but we can switch off our mod. And the next step is what's shown here. We now use again, optical pumping with 2 lasers, P1 and P2, to bring the atoms from here to the 3p1 state. So that's the second step to finally create inversion. Yeah, on the way of doing that, we are losing 75% of the atoms into other states, which we are not using. So that's another loss of 75%.
Which states are the M states, or?
Yeah, the M states we use the M=0 state as the upper laser state, the non-magnetic state, and the other states where we lose atoms to the M+-1. Okay. Yeah, these 2 states are basically useless for us, and well, to get rid of them, we shift them out of the way with a magnetic field that I have not said that yet. So we also have a magnetic field that's pointed out here. Here, this magnetic field is not yet switched on, but here we switch on a magnetic field, and that shifts the M=±1 states by a couple of megahertz away.
You don't really need this?
No, we don't want sort of incidental, we just want to have a clean situation where we know what's going on, only the M=0 atoms are in use. Okay, and then, well, this is what we see. So let's start with this back curve. This is the optical pumping pulse, but I have to say that, well, this doesn't mean that the inversion is only created here. The inversion is kind of finished at this point, at about 20 microsecond here. So the inversion is not instantaneous, as I sort of assumed in my model, but it turns out that it's a fairly good approximation if the production time of inversion is much below the delay time of the pulses. It's a good approximation to say basically it's like instantaneous inversion, only happening at a slightly later time. If you look at the theory, and I will do that a little bit in a moment, it turns out to be a pretty good approximation. Okay, so we create inversion around at 20 microsecond. And well, this is the exponential decay curve. It's better seen in this inset here. This is the typical exponential decay, and the blue pulse seen here would correspond to this spike that you see here. And then you see different pulses, and well, now comes an important point: how to evaluate, how to understand theoretically the different kind of pulses. And obviously, you know, the expectation is these pulses, including the corresponding delay time, depends on the particle number. The peak should scale with n squared. And obviously, we can measure particle number in our experiment, but not all that well. Maybe to like 5% or so, with an error of 5%, maybe 10%. Not so well. So what we do is actually we use the fact that we know that the pulse shape should be a secant, which can be very easily worked out from looking at a semi-classical theory. So you forget about the first quantum mechanical small time interval and assume that you have a little bit of electric field present at t equals 0, then you, by a very simple semi-classical laser theory, you can calculate that you expect a second pulse to come to existence. And this is how the second pulse look like. So B of t is the field in some units, and this is basically B squared is the photon number in the cavity, kappa is the cavity K. So we have 2 kappa here because we are looking at the intensity or the photon number, and you can calculate analytically that this is the expectation of what the pulse should look like. And we use exactly these curves to fit the data, and from that we get 2 numbers out. This is the number of particles that participated in this pulse and the delay time. And these are the numbers that we get from looking at these single short type curves.
Is this sort of a number weighted with the G of the position, or they are all in the right position?
Yeah, that's a good point. This is why we have the B in here, the bunching parameter. So in fact, we assume kind of an average of where the atoms are located in the mode. And your expectation is since, well, we have the magic lattice and we have well, the wavelengths of the laser transition, and these 2 wavelengths are not commensurate. So some of the atoms in the magic lattice don't sit at the right position. And if you calculate then it's obvious that the expectation is that the bunching factor should be 50%. So 50% of the atoms are not in a well, basically, the atoms that are not at the right positions sum up to factor 2 loss of coupling on average. But our data works better if you assume that B is 0.65. This turns out to be the best possible value for matching of the data. There's, after we have done all that, we found that there's an interesting paper by Blood and Bullich's group where they have a fairly educated calculation on how to evaluate the bunching factor, and turns out they also get the bunching factor of 0.65. Well, we didn't know that at this point. This came just out from the experiment. Okay, so now we have these kind of pulses with these 2 numbers coming out as quantities that we basically measure. And yeah, now we are interested in the pulse delay statistics, assuming first the case of instantaneous inversion, and later on we can expand that to include a finite time for the creation of inversion. But it turns out that this is already so the main theoretical ingredients that we need to understand our data. So we assume complete inversion at t equals 0. And then, well, we have to look at this picture to understand what is the expectation. Basically, the second pulse looks like that. At t equals 0, we have some amount of field, some strength of the field. And this field is, or you can also talk about numbers of photon number in the cavity that corresponds to that field. And this photon number is directly connected to the delay time of the classical pulse that you expect. So these 2 quantities, the size of the photon number here and the delay time or the peak, the time when the peak occurs, these 2 quantities are directly related in a way that you can calculate from your pulse shape. Okay, and this allows you to calculate the full statistics for for the arrival time of these pulses in the following way. You assume that at t equals 0 there is a process where this classical pulse is triggered by the first spontaneous photon. And so you assume that the rate of spontaneous photons scattered into the cavity at in this very close to t equals 0 must be this here. This is the Purcell factor, the bunching factor, which, well, accounts for the fact that the atoms don't all couple maximally. And there is the spontaneous emission rate, gamma, and the number of atoms that contribute. Okay? So this is the rate of spontaneous photons initially at t equals 0. And then you can evaluate the average intercavity photon number that corresponds to that rate by, well, sort of assuming a decay rate kappa for your cavity, and then this is the average photon number that well, tells you the size of this blue curve at this instance of time. And from that you can immediately calculate the delay time, and then you come up with this delay time probability distribution. So this is the probability that the pulse with a particle number n contributing to this pulse arrives at, or the peak of that pulse arrives at the time td. And this turns out to be what you can call a Gumbel distribution. This distribution has been described by a mathematician called Gumbel. I don't know, in the not the last, but the 19th century. So, some people call it a Gumbel distribution, and you see what it is. It's an exponential of an exponential. This is how it comes out. And from that, you can immediately calculate the average delay time, Td in brackets, and this is how it comes out. Logarithm of the particle number divided by the Purcell factor times the bunching factor times gamma times n. Okay, and then this can all be nicely compared with the data we have. So, well, first here I show you delay times versus atom number. So here we have changed the atom number, and as I told you, basically we post-select in the sense that we look at our pulses and then determine what is the atom number that belongs to that pulse. And then we plot these atom numbers versus these delay time or peak times versus the atom number, and we get this data here, and we can immediately plot the mean delay time that we get from our theory, and this is this curve here. So you see the data fit pretty well to our curve. We also can plot the errors, the statistical errors, these are the error bars you see here. But what turns out to happen is that if we subtract the theory, then there's a constant offset that remains. And this is the constant offset that accounts for the fact that we are not instantaneously at t equals 0 getting our inversion, but sometime later at 20 microseconds. And yeah, this is this red curve here. So what then we have done is to check whether the Gumbel distribution is the right distribution to describe the delay time statistics. So we've looked at two different particle numbers, 30,000 plus minus 5 and 15,000 plus minus 5. And then we've looked at many different pulses, putting together these histograms. These are the experimental data. And these lines they are basically coming from the Gumbel distribution that I've shown you before. And also there's a fairly okay fitting between data and the theory. Okay, so here we have looked at the errors of the arrival time, and there you see that there is for large for small particle numbers, there is a sort of a deviation. This is the curve that you calculate, directly calculate for instantaneous inversion, and then comes the problem that we are using a fairly coarse binning in our experiments because we need many pulses in each of these different classes to make the statistics good enough. And it seems, well, it's kind of a compromise. And from this finite binning, you make you basically make an error. So if you take that into account, then the theory curve looks like that. So you're approaching the data a little better. But even then, if you do that all right, there's still, for small particle numbers, there's a little bit of a mismatch. And sure, like if you go to small particle numbers, the pulse delay is longer, so there's longer time for bad things to happen. That's kind of our explanation. There are other disturbances, fluctuations, technical fluctuations that then are more important. That's our interpretation. Okay. So yeah, this is basically the last transparency, showing you how this all comes out if you account for a finite inversion process. So now, instead of having all the atoms in the excited state at t equals 0, we assume that there's some rate that we populate the excited state with, and we have to put that rate into our laser equation and sort of well, make the whole dynamics a little more complicated, but then we can no longer do all this nice, simple analytical calculations that a student can do in the third semester, but we have to do things numerically. But we can do that, and then this is a situation that you typically get. This is the inversion here, and you see now the inversion kind of takes some time to come to existence, and this would be the emitted pulse that belongs to this dynamics of inversion creation. And what one then finds, and this is interesting, is that if you do that and you subtract the analytical curve that I've shown you from the real theory in this case, then again you see that there's just an offset that you get, and this offset is exactly the 20 microsecond that we're seeing in the experiment. So it seems like it's a good approximation to say that if you are creating the inversion in a finite time, as long as you are well below the typical pulse delay time or pulse arrival time, then you can just assume that you still can work with an instantaneous creation of inversion, but happening at a later time. That's the outcome. Okay, so then I'm already as a summary. I've shown you our super-radiant lasing system with calcium, how we provide inversion, discuss the pulse delay statistics, and obviously in the future we want a CW mode operation of the system, and that's something that we well, have some advantages in our system since we have this specific way of creating our metastable atoms in the 3p2 mod. That might be pretty helpful to make that system continuous. And obviously a nice thing to do is using the 3p0 level instead of the 3p1 level. So these are the two points in our future program. And well, last not least, we have an opening of a PhD position in our cavity work. So if you're interested, address me, please, and you can choose what you want to, what you like to do most. It will be cavity. Okay, that's it.